Double angle identities. Here are the double angle identities. Sine of 2 times x is equal to 2 times sine x times cosine x. For cosine of 2x, we have 3 different versions. Cosine of 2x is equal to cosine squared x minus sine squared x, 1 minus 2 sine squared x, 2 cosine squared x minus 1, and then tangent of 2 times x is equal to 2 times tangent x all over 1 minus tangent squared x. Now you might be thinking, well, why are there 3 different formulas for cosine 2x? Well, sometimes for a particular problem, one version might be easier to use than another, but these are really all equivalent to one another. So if I focus on the top one, if I focus on cosine squared x minus sine squared x, what I can do is I can replace sine squared x with what I know to be true from the Pythagorean theorem. From the Pythagorean theorem, I know that sine squared x is equal to 1 minus cosine squared x. So from here to here, this is coming from the Pythagorean identity. The Pythagorean identity, sine squared x plus cosine squared x equals 1. So now here this negative will distribute, and I have cosine squared x minus 1 plus cosine squared x. So we have 2 copies of cosine squared x. We'll bring down the minus 1, and you can see how that's this last version of the double angle identity for cosine. And we can do something similar and replace cosine squared x with, again, a rewriting of the Pythagorean identity to get this middle double angle identity for cosine. So these are all equivalent, but for some problems it might be more beneficial to have one version over the other. Now, the last thing on here is there's a warning that I have, which is that if you have sine of a number times x, I cannot pull that number out to the front, right? So you can see directly right here how that doesn't work. So sine of 2 times x, sometimes students think I can pull out the 2 or like divide by 2, but you can see right here that's not what's happening. Otherwise we would just get 2 times sine x, but there's this extra cosine x here. So this is kind of one of the more common mistakes to see, is thinking that you can treat it as if sine is just a number or a variable when it's a function that doesn't have this property of being able to pull a coefficient outside of the trig function or put anything into a trig function. Before we use the identities, let's prove them, or at least let's prove one of them. So let's verify sine of 2 times a is equal to 2 sine a cosine a. So remember, we're going to start with one side of the equation and manipulate it to make it look like the other side. So I'm going to start by taking sine of 2 times a. And what I'm going to go ahead and start doing is rewriting 2 times a as a plus a. So here now a plus a is the same as 2a, but now that I have it as a sum on the inside, I can use the sum identity for the sine function, which says we take sine of the first angle, sine of a, cosine of the second angle, which also happens to be a, plus sine of the second angle, which is a, times cosine of the first angle, which is a. So we have sine a times cosine a plus sine a times cosine a, which is a total of 2 copies of sine a times cosine a. So we proved the double angle identity for sine using the sum identity for sine. In this example, we want to simplify the following expressions. In part A, we have cosine squared of 7x minus sine squared of 7x. Now, if this were a plus sign, then we know that we have the Pythagorean identity, and this would just equal 1. But since there's a minus between them, we don't have the Pythagorean identity. But we do have the double angle identity for cosine. So cosine squared of an angle minus sine squared of that same angle will condense down, so this whole quantity will condense down to cosine of 2 times the input of the sine or cosine function. So 2 times 7x, right? Double angle identity. We're doubling the angle. So this simplifies to cosine of 14x. So we took an expression with 2 terms and we simplified it down to 1 term. In part B, we have 6 sine of 15 degrees times cosine of 15 degrees. So here, we're going to use the double angle identity for sine. And the way that we know to do that is we see sine of some angle times cosine of that same angle. Now what we don't have in the front is that 2, at least explicitly, but we can factor 6 into 3 times 2, and then bring down the sine of 15 degrees, cosine of 15 degrees, so that we see that double angle identity for sine more clearly. So when we have 2 times sine of an angle, cosine of that same angle, that's going to become sine of 2 times the angle. Right, sine of 2 times the angle. We're going to have to bring the 3 down. The 3 didn't disappear. The 2 did. The 2 got like swallowed up into the identity, right? 2 sine A cosine A shrinks down to sine of 2A. So A, the angle, is 15 degrees. The 3 gets brought down. So we have 3 times sine of 30 degrees. So this is already more simplified, but we can do better than this because sine of 30 degrees is a value we can evaluate. So we have 3 times 1/2, or 3 over 2, is our simplified answer. In this next example, we want to find sine of 2x, cosine of 2x, and tangent of 2x, given cosine x equals 3 over 5, and sine x is less than 0. So we want to find sine of 2x. So sine of 2x from our identities that we just learned is 2 times sine x times cosine x. So what do we have? We have the value of cosine x. Cosine x is 3 over 5. So we have 2 times, and we're missing sine x, and then cosine x is 3 over 5. So we're missing the value of sine x. We do know sine x is a negative value, but we need to know specifically what value it is. And here's where we're going to have to draw ourselves a triangle. So if cosine x is 3 over 5, so cosine is positive and sine is negative, right? So cosine x is greater than 0 and sine x is less than 0, then x is in quadrant 4. That's where cosine is positive, but sine is negative. So we're going to think about drawing a triangle in quadrant 4 so that we can find our missing side length. So here's x, and what do we know? Cosine is adjacent over hypotenuse. So here's 3 and here's 5, the adjacent side, the hypotenuse side. So we're missing the opposite side, which is 4. But it has to be negative because it's going down, because this is going to be a 3, 4, 5 right triangle. Now that we have the triangle drawn, we can find sine of the angle because that's opposite over hypotenuse. So we're going to plug in negative 4 over 5. And then if we multiply all this out, this is like 2 over 1, so we just multiply across all the numerators. We have negative 8 times 3, so negative 24 over 5 times 5. Negative 24 over 25. Now let's go ahead and find cosine 2x. Well, for cosine 2x, we have different versions, right? And we do have both the value of sine x, which is negative 4 over 5, and the value of cosine x. So we can use any version we want. But the one I am going to go ahead and use is 2 cosine squared x minus 1. And the reason is just because I know for sure the value of cosine x. Like maybe I made a mistake drawing this triangle, so I don't want to use sine x. I mean, I could because I didn't make a mistake, but we essentially could have found cosine 2x without drawing a triangle at all if we use this version of the double angle identity for cosine, the one that just depends on cosine x, since that's the value I'm given. So we have 2 times 3/5 squared minus 1. So this is 2 times 9 over 25 minus 1. So that's 18 over 25 minus 25 over 25, so that I have common denominators. So I get negative 7 over 25. And then finally, I'm asked to find tangent of 2x. And there is a double angle identity for tangent, but since we already have sine of 2x and cosine 2x, we can take tangent 2x to be the quotient of sine of 2x over cosine of 2x. So I'm going to go ahead and put over here tangent 2x. Well, that's sine of 2x over cosine 2x, which is negative 24 over 25 over negative 7 over 25. So if I multiply by the reciprocal, the 25s will cancel, the negatives are going to cancel, and we have 24 over 7 as the value of tangent of 2x. In this example, I want to find cosine alpha given cosine 2 alpha is equal to 1/4 and alpha terminates in quadrant 2. So this is just a fancy way of saying alpha is in quadrant 2. So we want to find cosine alpha, and we're given cosine 2 alpha is equal to 1/2. So I'm going to start with the warning, because I definitely see this more often than I should see it, or more often than I want to see it. I see a lot of this. So cosine of 2 alpha is equal to 1/2. Okay, well I want cosine alpha, so I'm just going to divide both sides by 2. That's the exact thing I cannot do, right? So I see students just divide both sides by 2 or multiply by 1/2 and cancel. Ooh, I cannot do that, right? I'm not allowed to essentially put something into a trig function, right? I'm not allowed to do that, to just get myself to cosine A. So let's go ahead and erase that. So what do we have to do here? Well, what do we know about cosine of double an angle? We have 3 different versions of this, right? We have cosine of 2 alpha, we have cosine squared alpha minus sine squared alpha. Well, there's no sine at all in this problem. So it says I want to find cosine of alpha, so I don't want to use this version. And I know cosine 2 alpha is equal to 1 minus 2 sine squared alpha. Again, I don't have sine involved. I'm not being asked for sine alpha. Otherwise, this would be a good one to use. So I'm not going to use that one. I'm going to go ahead and use cosine 2 alpha is equal to 2 cosine squared alpha minus 1. So I'm going to use this version because I want to find cosine alpha, right? And I have cosine 2 alpha, that's 1/2. So over here, I'm going to go ahead and fill in the left side with 1/2, right? So the left side, cosine 2 alpha, right here is equal to 1/2, and then equals 2 cosine squared alpha minus 1. And I'm solving for cosine alpha. So I'm going to add the 1 to the other side, right? So 1/2 plus 1 equals 2 cosine squared alpha. So 1/2 plus 1 is 3/2. And then I'm going to go ahead and divide both sides by 2 because this 2 is on the outside, right? So this is 2 times cosine squared alpha. I can divide both sides by 2 or multiply by 1/2, kind of however I want to think about this. So if I multiply both sides by 1/2, since on the left side I had a fraction, I have 3/4 equals cosine squared alpha. All right, so now I want just cosine alpha. I'm going to take the square root of both sides. So I get plus or minus the square root of 3/4 equals cosine alpha. This is 2 different answers. I can't have 2 different answers, so that's where I look to the fact that alpha terminates in quadrant 2. In quadrant 2, we know only the sine function is positive. So that means we're going to take cosine alpha to be negative the square root of 3 over 2. So the square root of 4 is 2, so I can simplify that part, and I get this as my answer. In this example, I want to evaluate cosine of 2 times sine inverse of 2 over 5. So I want to look to the inside of this composition of a trig and an inverse trig function. And specifically, I want to focus on the sine inverse of 2 over 5 part. So the first question is can I find what angle I plug into sine to get out 2 over 5? And the answer is no. This is not one of our typical reference angles. So instead, I'm going to recognize that this is an angle, sine inverse of 2 over 5. The answer would be some angle, let's call it theta. So I'm going to write this as cosine of 2 theta. Alright, so now I know that theta is equal to sine inverse of 2 over 5. Here I can take the sine of both sides, so I get sine theta, sine of sine inverse cancels, so I just get 2 over 5. Right, or essentially write out the definition of an inverse. So sine of theta equals 2 over 5. So this is what I know. So over here, cosine 2 theta, I have those 3 different versions of the identity for cosine. I'm going to choose the one that only involves the sine function because that's the value that I have. So here, cosine 2 theta is 1 minus 2 sine squared theta. So I can simply plug 2 over 5 into sine theta right here. 1 minus 2 times 2 over 5 squared, and then simplify. So 1 minus, let's see, this is going to be 4 over 25. 2 times 4 is 8, so 8 over 25. We'll rewrite 1 as 25 over 25. So we get 17 over 25. Now, if I chose to use the first version of cosine 2 theta that we learned, which was cosine squared theta minus sine squared theta, then I would need to draw a triangle to find the value of cosine theta, and I'd still get the same answer, but I just made more work for myself. So in knowing all of the versions of the double angle identity for cosine, I'm making a lot less work for myself to find the answer. In this next example, we want to write sine of 2 arccosine x as an algebraic expression of x. So here, sine of 2 arccosine of x, well, we're going to focus on the arccosine of x part. We know that that's going to be some angle theta. So that this problem will become sine of 2 theta. Well, we know sine of 2 theta is 2 sine theta times cosine theta. Now, I'm going to pull this piece of information off to the side that we said at the beginning. Theta is arccosine of x, which means that cosine theta is equal to x, or x over 1. So I can replace cosine theta with x, but I still need to find sine theta. So over here I have 2, I'm going to leave a blank space, and then cosine theta is x. So we're starting to turn this into an algebraic expression of just x by replacing cosine theta, but I also need to replace sine theta. So I am going to need to draw a triangle. So that triangle is going to look like a right triangle, the angle is theta, and we have adjacent is x over hypotenuse is 1. So this missing side length here from the Pythagorean theorem is going to be the square root of 1 minus x squared. So the hypotenuse minus the other side length squared, all underneath the square root. And so if I want sine of theta, that's opposite over hypotenuse. So opposite is this square root of 1 minus x squared. So here, cleaning this up, we'll have 2x times the square root of 1 minus x squared. As our algebraic expression of x, there's no trigonometric functions left in it. Here we want to verify the following identity. So cotangent x times sine of 2x equals 1 plus cosine of 2x. So we can take one side and manipulate it and get it to look like the other side, or we can work on both sides separately until we get them to look like the same thing on both sides. So that's going to be the approach that I take, just because I already see that the left side and the right side have a double angle identity involved. So I'm going to want to work on each side here. So what I like to do is just put a big vertical line below the equal sign to remind myself I can't do anything like multiply both sides by something, because then I'm assuming equality and I'm trying to prove that this left side does equal this right side. So on the left side, I'm going to start to rewrite things with the known identities I have. So cotangent is cosine x over sine x. And sine of 2x is 2 times sine x times cosine x. So here I can cancel the sine x's. Sine x over sine x is 1. And what I have left is 2 cosine squared x. And on the right hand side, I'm going to go ahead and start working with that and kind of see if I can make it look like the left hand side. So I'm going to put 1 plus, now cosine 2x has those 3 different versions. I can see what I'm aiming for though. The left side is cosine 2x, so I'm going to use the version that involves just cosine x, which is 2 cosine squared x minus 1. So now if we see what happens, the 1's cancel out and I have just 2 cosine squared x. So that's it, I'm done. I have verified that the left side equals the right hand side. And the last thing we're going to talk about are the power reducing identities. So if I have something that looks like sine squared x, this is a power of sine that's greater than 1. It's a power of 2 of the sine function. But I can rewrite sine squared x to be 1 minus cosine 2x all over 2. Thereby reducing the power of the trig function. I went from a power of 2 trig function to power of 1. This is cosine to the first power. If I start with cosine squared x, the only difference is that this is 1 plus cosine of 2x all over 2. So I'm still going from a higher power of a trig function, cosine squared, and taking it down to cosine to the first. Now, these come from the double angle identities. That's why we're talking about them in this section. So to show that, I'm going to start with one version of my double angle identity for cosine. So cosine of 2x is 1 minus 2 sine squared x. If I solve this for sine, I'm going to get cosine 2x minus 1 equals negative 2 sine squared x. And I just want sine squared x. I'm going to divide both sides by negative 2. So what I end up with here, I'm going to move the negative that's on the bottom to the top and distribute it. So I have negative cosine 2x plus 1 over 2 is equal to sine squared x. Right, because in quotient, I can take the negative that's on the bottom and I can move it to the top. There's 2 terms on the top, so it would distribute. So I can see here, I can switch these with the commutative property. This is 1 minus cosine 2x over 2 is equal to sine squared x. So that's the power reducing identity. Another way that we could see this written is this could be thought of as 1/2 times 1 minus cosine 2x is equal to sine squared x. So just thinking about taking that 2 on the bottom, rewriting it as 1/2 times the numerator. This is another way to think about the power reducing identity. And the other one could be derived if we start with the different version of the double angle identity, the one involving just cosine. In this example, we are told to write an equivalent for cosine to the 4th of x that does not involve any powers of sine or cosine greater than 1. So essentially, we want to reduce the power. I don't want to work with cosine to the 4th of x, right? I want to work with all sine or cosine to the first power. So we're going to start by taking that cosine to the 4th of x, and we're going to rewrite it as cosine squared x times cosine squared x, because that's the power reducing formula, how it starts, cosine squared. So now the power reducing formula for cosine squared looks like 1 plus cosine 2x over 2 times 1 plus cosine 2x over 2. So make sure that you're very clear about the difference between cosine squared x and cosine 2x, right? Making sure that it's clearly up in the exponent when it's squared, and then clearly the same size and the same level as x when it's cosine 2x. Okay, so now here I have binomials on the top, so I'm going to keep them in parentheses. All of this is multiplied. On the bottom I have 2 times 2, which is 4. So what I'm going to do is I'm going to go ahead and pull a 1/4 to the front, and just think about this for a second as 1 plus cosine 2x times 1 plus cosine 2x. And what you might be thinking is, we're done. I don't see any powers of sine or cosine greater than 1. This is cosine to the first, this is cosine to the first. But it is implied here that this is multiplied out because these are two factors, and when I multiply it out, cosine 2x times cosine 2x gets us cosine squared 2x. So what I unfortunately have to do is multiply it all out and then reduce down that cosine squared 2x. So I'm going to leave the 1/4 just kind of hanging in the front. And then I'm going to put a big set of brackets here for a second. I'm going to go ahead and distribute all this. So 1 times 1 is 1. Outer is plus cosine 2x. Inner is plus cosine 2x. But then last, cosine 2x times cosine 2x is cosine squared of 2x. There's 2 copies of cosine 2x. So now these combine together. So I'm going to have 1/4 times 1 plus 2 copies of cosine 2x plus cosine squared of 2x. So I have one more power reducing to do here. Get rid of this cosine squared of 2x. So I'm going to go ahead and bring this up here. So I have 1/4, 1 plus 2 cosine 2x plus, all right, so now how do we work with this? Cosine squared of 2x. So the formula that we have, I'm going to rewrite it on the top for a second. I have that cosine squared, I'm going to do something that looks kind of funny. I'm going to say cosine squared heart is equal to 1 plus cosine 2 heart over 2. And that's because the x that's there, or theta, is just a variable. So I can choose to put whatever I want there. So I can go ahead and put a heart there. And so it just would get replaced in the formula with the equivalent value. So I want cosine 2x, cosine squared 2x to get reduced. So that means this would be cosine squared of 2x. So 2x is going to replace that heart right there. So this is 1 plus cosine of 2 times 2x over 2. Because I replaced heart with 2x, so in the formula I have to replace heart with 2x. So then this is 1 plus cosine 4x over 2. So cosine squared 2x is 1 plus cosine 4x over 2. So that's what I'm going to go ahead and plug in right here. 1 plus cosine of 4x all over 2. Okay, so now from here we're just going to do some simplifying because we do have all powers of sine or cosine that are to the first. Like there's nothing that's higher than a sine or cosine to the first power here. So now it's just a matter of cleaning it up a little bit. So let's see, we have 1/4, we have 1 plus 2 cosine 2x. I'm going to go ahead and split this up right here into 2 separate terms. So this is plus 1/2 plus 1/2 cosine of 4x. Then I'm going to distribute, actually, I can combine 1 and 1/2 together. Maybe let's do that part first. So I have 1/4. 1 and 1/2 is 3/2 plus 2 cosine 2x plus 1/2 cosine 4x. It's all just a little bit of arithmetic and algebra. So distribute the 1/4. I get 3/8 plus, if I distribute the 1/4 times 2, I get 1/2 cosine 2x, and then 1/4 times 1/2 is 1/8 cosine 4x. So this is my answer. And you might be thinking, okay, thank goodness we're done. But you also might be thinking, why did we do that? Like, we started with this super nice little tiny one term, like cosine to the 4th of x. Why would we make it this ugly thing right here? And I understand where you're coming from, but this is actually easier to work with when it comes to integration. So this is a technique that we would use to rewrite this higher power that we don't want to deal with, because we do have some nice rules that we can use in a calculus course to integrate. So that's one of the reasons why we might want to reduce a power and make it this uglier thing, because it is easier to work with in a different class and a different application.